SwayamPrabha. Digital India. Educated India.
Hello again. So, we are talking about the properties of the function space, right. So, we took this simple example of a taut string and we wanted to know what kind of shapes this taut string will take when you apply different kinds of forces on it, right. So, all of those we have to search in order to find one that minimize the potential energy. So, we are talking about that function space here. We say what kind of function? We said that they need not be continuous like this, they can be they need not be differentiable like this smooth, they can be non-differentiable like this kinked one, which is what happens in this particular case when there is a force like that, right. We also said that if you take this particular case, there are two wedges that squeeze this wire, so that it will have a discontinuity over here. Okay, let me change color. So, we have here a discontinuity, right. The same x value has a range of values. So, this type of things are also allowed, so things that have discontinuity. So, now our function space consists of what? Does it contain tomatoes or oranges or apples or what, right? They are not continuous, okay? They are not differentiable, right? So, what? Anything can be belong to this function space. So, we can find our answer here. That is not true. So, there are certain properties that you can define, so that your function space is properly characterized. So, you know where you are searching. Okay. You are searching in a room, you have to know what kind of a room that is. Okay. So, for that we need to understand what is called a normed vector space, okay, and some properties of that. We know what a vector space is now. Now, we add a qualifier called normed. Right. What does it mean? It simply means that along with a vector space there is something called a norm also. Norm is like a metric, something that says something about it. There are some people, let us say there is a norm, we say if we can measure the height of every person, weight of every person, let us say, then there is a norm. Okay. You can talk about two different people there and what is the distance between them, that is the norm. So, norm is mathematically defined or denoted, let us say like this. If I take this f of x here, so when we say something is a norm, it talks about a characteristic of that, like height of a person, like I said. A norm is defined as in a vector space is a real valued function. So, this x that we put like this, okay, is a norm. It should be a real number, it should belong to this real number space R. So, you have a function space, okay, let us call this a function space, okay, and then we have the real number space, right. So, norm takes a function and maps it to a real number, we can calculate it, that is what is a norm. So, when you have a norm defined for a vector space, we get what is called a normed vector space. That norm has to satisfy 4 properties that are shown here. First is that the norm has to be non-negative, just like metric is. Metric should be non-negative and so is the norm, both are the same. Okay. And if the norm of an element belong to vector space is 0, that means that that element should be a null vector, the 0 function in that. Okay. Similarly, the norm of alpha times x is equal to absolute value of alpha times norm of x, and then we have our triangular inequality equivalent here, x plus y norm is less than or equal to norm of x plus norm of y. Okay. There are the 4 things that the norm has to satisfy. If you want to come up with your own norm, you should make sure that all these 1, 2, 3, 4 properties are satisfied for any 2 elements or any scalar element, that alpha which belongs to scalar field should satisfy these 4 properties. So, now we said already that our function space is like a vector space. So, space of all continuous functions is a vector space because it would satisfy those properties, and there is a norm for that. Okay. We can have a normed function space such as this one, and you can have differentiable functions, okay, that we have C1 continuous. So, we have not only continuous, we can also have say that the derivative is also continuous, what we call differentiable, and for each of them you can define different norms. Okay. There are lot of different norms that you can define for the same space. All right. So, like I said, function analysis is the one that covers all these things in detail. What you are talking about is only a basic understanding of various terminology in the context of our optimization or calculus of variations, right. Calculus of variations is optimization over the function spaces. We need to understand what role these different terminology are going to have. Okay. So, one of these spaces we say normed vector space. So, we said vector space or a function space that has a norm defined on it. So, something you can say this element, that is a characteristic, that is a norm. Now, let us talk about something else called Banach space, right. So, again the motivation for this comes from our notion of. So, we said that in this particular case what should be our function space, what kind of thing, not continuous, not differentiable, so what, right. So, for that we want to define what is called this Banach space. So, what is the significance of it? This has a lot of significance in calculus of variations. Okay. Let us see the definition first and then come back. This Banach space, as you see the definition here, it is a complete normed vector space. Okay. So, complete I have underlined. So, we have to understand what we mean by complete. It is a complete normed vector space, that is called a Banach space, right. This completeness, there is a definition for that also. A normed vector space X is complete if every Cauchy sequence from X has a limit in X. Then you have to say what is Cauchy sequence, what is limit, and so forth, right. A Cauchy sequence is basically a converging sequence, that is what is the definition here. What it says that you can have a sequence, meaning that if you start with a function, we talk about function spaces, they are also vector spaces, right. You have functions, if I start with a function and I have something, a rule or operation that gives me a next function, the next function, and next function, then I get a sequence of things. Such a sequence converges, that sequence is called a Cauchy sequence, and a convergent sequence will have a limit, it will stop somewhere, right. That limit should belong to that space. If it does, then we call such a thing Banach space. Okay. That is what all this mathematics in this slide and this slide, but that you can read leisurely. What it says is that you have a vector space or a function space. Okay. Function space is just one kind of a vector space, right. You have a function space, and that there is a norm also, that is you can, for every function you can define a characteristic. Now, that function space will be called Banach space if it is complete normed vector space. Complete means that there should be some converging sequences which are called Cauchy sequences, and the limit of sequences should lie within the space. Such a thing is called a Banach space, right. And this is important in calculus of variations because we want to find a function that minimizes your objective functional, right. We understand what a functional now is, right. We have to minimize that functional, we have to find such a function. So, when we search in a space, okay, there are a lot of functions. Now, these are not points, these are all functions. Okay. When you have so many functions, if I start a sequence, I choose this one, I call it 1, I choose this 2, I choose this 3, I choose this 4, and so forth. So, I will have F1 and then F2, F3, like that. Let us say there is Fn. So, let us say after that how many more things I take, the value of this will there will be a limit, in the sense that that kind of function will not be different from Fn plus 1, Fn plus 2, and so forth. That means that this sequence of functions has converged. Okay, I have fn plus 1, they are all identical. So, if I n plus 2, they are all the same, let us say almost the same within some tolerance, right. Such a sequence of functions we call it a converging sequence, and the limit of that this thing what I converge. So, that also should belong to this space. If it does, such a thing we call Banach space. Okay. That is a complete normal vector, complete meaning that limits of all convergent sequence belongs to that space itself. Why is it important for us? It is important for us in calculus of variations, because if I have Brachistochrone problem, point A to B, I want to find in the presence of gravity a function that minimizes the time, which is a cycloid, but before that let us say randomly I take another function. Okay. From there let us say I start my initial guess 1, and that may take me to another function LO, and then let us say that is second function, and then I take some other function, I can call it 3, 1, 2, 3 and many more functions. Finally, I converge to my y star here, right. After that there is nothing further to go, that is the best, right. So, this converging sequence has a lot of role to play in calculus of variations, right, and that final function should belong to the function space that I originally took to search, right. We are searching in a space which should contain our solution. That means that somebody has to search for something in a room, the first thing you should ask is, do you know for sure that the what I am looking for is in that room, right. If it is not there, it is a futile search, right. So, our optimization or calculus of variation we do to minimize a functional, we should search in a room called Banach space, okay, that is what it means, all right. So, we need to have the answer in the room that we are searching it, okay, that is what it actually means, right. So, there is another space called Hilbert space, right. The Hilbert space has a different thing, what is called here a complete inner product space is called a Hilbert space. What is a Hilbert space? It should be complete inner product. What is inner product? Inner product we can define as shown here, right. So, norm we needed element itself x, and we put 2 bars on it saying the norm, right. So, if I go back here, all right, let us go to the next page. Yeah. So, if I have a function space, I have different functions. I have f1 of x, let us say f2 of x, and then f3 of x and so forth. So, all of these are points in that function space. So, for every one of them we can define a norm. A norm can be a norm of a function which we say we have this f1, we have a norm on it, right. It can be an integral. So, if the domain is from x1 to x2, I can say f1 of x dx, a real number, norm should be a real number, I can define. So, similarly I can define for f2 also, f2 norm is x1 to x2 f2 dx, right, like that I can have a norm. So, as opposed to this which talks about if I take a f1, norm of f1 tells me something about f1, just like in a population, a group of people, norm can be height of the person, right. For every person there is a height, every person there is a weight, those are norms. So, you can take one element of the function space or vector space and talk about norm. But the one that we now talk about, which is called the inner product, okay, inner product, that requires 2 elements, that is if I have a function space, okay, let us say there are f1, f2, f3, f4, f5 and so forth, right. In order to define an inner product, I need 2 things. I can define inner product between f1 and f2, we put 2 year brackets, that is inner product, okay. Like if you have 2 vectors, dot product is like a inner product. Two vectors meaning our mechanics vectors. If I say there is V1 is a vector, normal mechanics vector, and there is a V2, I can put dot product, right. So, that dot product is an inner product. If you want to recall, let us say I have V1x plus V1y j like a two dimensional vector. When I say dot product V2x plus V2y, if I have, you know how to do dot product, basically V1x times V2x, because I dot with I will be 1, I dotted with j will be 0, and then j dotted with I will be 0, j. So, we will basically get V1x V2x plus V2 V1y V2y, that is a dot product, that is the inner product. Okay. It is just that it is defined not for simple vectors such as our mechanics vectors, they are defined for these vectors which are functions. For functions also you can define inner product. It can be as simple as, there will be again 4 properties for that. Let us say I can say x1 to x2, I can say f1 times f2 dx, that is inner product. It satisfies certain properties which are listed here. When you see inner product, x plus y z should be equal to xz plus yz, and then alpha x times y, alpha x and y, alpha times x and y should be equal to alpha times xy inner product, and then xy should be, for when you talk about complex numbers, it will be yx also, that we do not need when we are dealing with real numbers, and then xx is always greater than or equal to 0, means non-negative. When xx is equal to 0, that is only true if x is equal to the x is the null function there. Okay. There is a relation between inner product and the norm, such as this, you know, when you say inner product of the element with itself, then that will be the norm, right. Why do we need this inner product? When you had a norm, I said that is a characteristic like a height of a person or a weight of a person or something like that. Why do you need between two people? When you want to compare things, you need to have. What kinds of things do we compare? One of the things is the orientation. Normal mechanics, when you say dot product is 0, that means that those two vectors are perpendicular to each other, right. So, it talks about that kind of an angle between two vectors. Similarly, for functions also you can talk about inner product space. So, that is the Hilbert space, and a this Banach space and Hilbert space also be complete inner product space, meaning that if I take a sequence of things that reaches a limit, that limit should belong to the Hilbert space, right. So, complete inner product space is a Hilbert space, and this Hilbert space and Banach space are important in our optimization. As I said that whatever space we search or a room we search should be a Banach space. So, Banach space, Hilbert spaces are not particular spaces, but they are kind of category of spaces, like we can say Banach space are vegetables and Hilbert space are fruits, right. We are not saying which vegetable, we are not saying it is brinjal or lady's finger or some other gourd, but we are saying all of them are vegetables, they are Banach spaces which have a norm and complete normed vector space. Hilbert spaces has inner product and they are like fruits, we are not saying apple, orange or banana, but they are all fruits, right. Now, we will talk about a few specific spaces as well, such as the one which I have shown, Lebesgue space. See, Banach space and Hilbert spaces are generic spaces, categories, let us say fruits and vegetables, that is all. This is either a fruit or a vegetable. If it is a Banach space, it is of one kind, Hilbert space of another kind, which satisfies this properties we defined, one with the norm, other with the inner product. When you say Lebesgue space, which is important, going back to our the string problem, what function should we take, right, that is where we are getting. Now, this Lebesgue space has a particular norm associated with it, which is defined here, right. The Lebesgue space is contains all these elements V such that a particular norm on it over here, right, that is norm, that we have this V and 2 bars like this, right. That norm has a subscript here which is saying LQ over some domain, right, that should be less than infinity we are saying. All we are saying is that the Lebesgue norm, which is what is defined here, the Lebesgue norm should be finite. If you go back to our string problem, if you recall. So, we said what kinds of things will be here, right? Not any discontinuous thing, but things where this Lebesgue norm is less than infinity, meaning finite. When we apply these forces on the string, we do not want this string to go to infinity, right. It is some kind of energy in it should be finite. It should not be indefinitely having a lot of strain energy or potential energy, right. It should have a finite one, and that is what we have here. Okay. When we say this Lebesgue norm, that you should be finite. So, what it is saying is that the Lebesgue norm is finite. It is saying not infinite, less than infinity, it is finite, right. What is Lebesgue norm? Look at this integral. So, it is integral of the absolute value of v raised to q, where q is some number, right, and integrate that, integrate the absolute value of v raised to q, and then take the qth root, that is a Lebesgue norm, right. That is kind of some quantity, right, but that is not enough for mechanics, and q can be 2, that becomes what we call L2 norm, like a distance, okay, like a function f square dx integral, integral of f square dx is like what is called L2 norm, right. These are all Lebesgue norms, and it will become more clear to you when we talk about a more complicated thing called a Sobolev space, which has a Sobolev norm, okay, the Sobolev norm, which is a little bit more complicated, right. It is a, there is a summation here over alpha such that its absolute value is less than r, okay, and then we have a norm which has this d raised to alpha v. The d is basically differential operator. If alpha equal to 1, it is a first derivative, alpha equal to 2, it is second derivative, alpha equal to 0, it is a function itself, that v itself, right. But here we are not saying alpha should be integer, even fractional derivatives are allowed, which we are not going to get into, but know that fractional derivatives also you cannot, you do not need to have dy by dx and d squared y by dx square, you can also have something in between them like derivative 1.3, 1.4 or whatever, right. So, it says that all of those if you take and raise it to q and take the norm and sum them all up and take the qth root of it, then you get what is called Sobolev norm. Why is it important for us? It looks very abstract. It is important for us because our functionals are going to be containing function and their derivatives. That is exactly what this is saying. Whatever we have here, what it is saying is that summation of something, right. So, function and its derivatives, summation can be an integral. The norm here already, what we have the norm here, that can be an integral, need not be the only kind, it can be other things we have seen already. It is something that sums up the whole function, okay. So, this Sobolev space that we talk about is an energy space, because most of the strain energy, potential energy, they all contain the function, its first derivative and second derivative and so forth. Normally in mechanics you do not go beyond second derivative, but you can in principle. There are energy spaces where those energies are finite, because if you see Lebesgue norm, we said that should be less than infinity, you cannot have infinite strain energy. That is why the Sobolev space are important. So, in calculus of variations, when we apply to mechanics in our variational methods, we should ensure that our functions belong to Sobolev space. By the way, Sobolev space is a Banach space that all been proved by Sobolev and others. Sobolev space is named after a person called Sobolev, and so is Lebesgue and Banach and so forth. It is a Banach space, meaning that Sobolev, if we call Banach space as a space of vegetables, Sobolev space is a particular vegetable, that is like let us say a brinjal, and Lebesgue space is let us say a snake god, right. These are particular spaces, whereas Banach space is like a vegetable. Similarly, Hilbert space also, there will be several specific spaces can be there, okay. Having understood these spaces, now let us take another definition of functional before we leave it. We said a functional is simply a mapping from a function space, which we understand a little bit more than we knew before, to a real number space. So, basically this definition says that a function is a transformation from a vector space or a function space. So, when I say vector space here, I also mean this to be a function space. Okay. To coefficient field, meaning that k that we have, right, real number. Okay. Once you understand that functional in that manner, basically it should go from functions that belong to certain space which satisfies all this Lebesgue norm or Sobolev norm and so forth to a real number space. Okay. That is what a functional does. For everything here it takes you there, that is a functional. Normally people sometimes quickly define a functional as function of functions. That will be incorrect, because if f of x is a function, f square, okay, which is a function of function, that is not a functional, right, but a functional should take a function to a real number space, that is what is a functional. Once we talk about a functional, we understand, and we can talk about linear function. That is like once we understand function, we can talk about this linear function, nonlinear function. What is a linear functional? Something that satisfies this. Okay. J, if I say j of x is a functional, j of y is another functional. If j of x plus j of y is equal to j of x plus y, then it is a linear functional. Similarly, j of alpha x is equal to times j of x, then that is a linear function. Both of them can be put together in this fashion here. J of alpha times x plus beta times y should be equal to alpha times j of x plus beta times j of y, then such a functional j, we call it a linear functional. Okay. And bounded functional, where that is bounded by a number c times the norm of that function. Okay. So, that is a bound, that is also important for us in calculus variations. Whenever we take a functional which we want to minimize, we want it to be bounded, we do not want it to go to infinity indefinitely, that will cause problems. So, we need to have bounded functionals, and finally we need continuous functionals as well. We know what continuous functions are, right, a function that has a value, if you perturb a little bit here, there will be, so every function will have what we call a domain and a range, right, this is the input, that is the output. If I have some here, there is a corresponding thing there. Now, if I perturb a little bit in the domain, the range should not be going over there, it should be somewhere close by. If there is epsilon here, there should be distance within delta. Okay. If this epsilon is around that point, if I am there, that should be there, that is a continuous one, right. So, similarly for function also we can talk about something called a continuous functional with the same kind of notion that we have, right. So, if I have a functional j is said to be continuous at x in D in open set, all those qualifications exist, open set and all that, right. If j has a limit j of x at x, or symbolically as y tends to x, a little perturbed point in the domain, then j of y should tend to j of x. So, in the domain if they are tending to each other, in the range also they should. Such a thing is called a continuous functional. Okay. So, to summarize today, let us show here. Let us just, yeah, a few things that we talked about. We talked about what is called a functional, and we defined metric spaces and vector spaces. Vector space will have a scalar field associated with it, and it needs vector addition, two of them, two vectors, elements of that you will be able to add following some rules, and also scalar multiplication, meaning that something that belongs to the scalar field which we called k, something that belongs to vector space, I can just call it capital X. I should be able to add two elements of x, that is a vector addition. I will multiply a number belonging to k with x, right. So, we discussed this vector space, and then we talked about norm, and then we said normed vector space is called Banach space, normed vector space right, a complete non-vector space, right. So, in that sense all the converging sequences should belong to that is our Banach space. We also talked about inner product and complete inner product space is called Hilbert space, and these are generic categories of spaces, okay, which is Banach is especially important because whatever initial guess we start with a function, when you generate a sequence of things iterative optimization, the limit or converging function should be within that space. Okay. Again remember, when you are searching in a room, at the end of the search you should still be in the room, not outside, that is Banach space. Hilbert space talks about relations, whether things are perpendicular or not aligned and things like that. Okay. That we do not need so much in optimization that we are going to talk about. Banach space is an important thing, and then we also talked about Lebesgue space and Sobolev space, okay, which are important things in terms of mechanics, because both of these, especially Sobolev space, they are called energy spaces, okay, or we can call finite energy spaces, right, because we saw that should be less than infinity, okay. Like the string problem, you cannot have indefinitely infinite energy, it needs to have finite energy, then all such functions which give rise to finite energy are the ones that you should be searching, okay. With these preliminaries we will jump into calculus of variations in the next lecture. Thank you.